Hi, my name is Brian Caffo, and this is the class on residuals, diagnostics and variation in the Coursera regression class, taught by myself, Jeff Fleek, and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so just to remind ourselves of some notation, we specify the linear model this way as the sum of a bunch of linear effects from the covariates multiplied times the parameters. As we need here, we're going to assume that the errors are IID normal 0 sigma squared, and then we define the residuals as we did before. EI, notice there's a difference between EI and epsilon I, right? Epsilon I is the true error, and the EI are the observed residuals, are the difference between the observed data point and the fitted data point, where the fitted data point is merely our regressors, but then multiplied times the fitted beta values. Our estimate of the residual variation is just the average squared residual, where instead of dividing by n, we divide by n minus p for unbiasedness. Okay, so hopefully this none of this is a great stretch. Given everything that we've accomplished in linear regression, none of this should seem so bad. Now, let's look back at the Swiss fertility data. And so you can do data Swiss. And par MFRO C22 just says I want 4 plots arranged in a 2x2 array. I'm going to fit my linear model, and I'm just going to include all my covariates. And I'm just going to say plot fit. And it gives us these set of different plots, and what we're going to talk about today are what these, basically what these plots do and why someone would want to plot them, right? So this is, they're assessing different things, different aspects of model fit. Okay, so let's talk a little bit about outliers and influential points. So consider these 4 orange points here. So this one's easy. It's sort of right in the middle of the data. It probably isn't very influential on the model fit, and it isn't very deviant from the model behavior. Anyway, this guy probably isn't very influential because it's right in the middle of the data cloud, in the middle of the x values, but it is very aberrant relative to the what we kind of perceive to be the model. This guy has a lot of potential for influence in that it's not around the data points at all, the x data points at all. So remember our regression line has to go through that middle x bar, y bar point. So a point out here, has a lot of potential for influence. It's almost like if this was a fulcrum and this is the bar, as you get further out on the bar, it has a lot more force to be able to move the line. So this one has the potential for a lot of influence, but elects not to exert it by fitting in nicely with the model that the rest of the data define. And then this guy is, if we were to have included this guy in the fit, the regression line would move down. This guy is both influential by not being in the data cloud of x's, outlying in the sense that it doesn't seem to appear to fit the model terribly well. Okay. So let's just talk about all these different aspects of what it means to have an outlier of a different sort or an influential point of a different point. So first of all, let me point out, calling a point an outlier is vague. And that's what we're going to talk about today, is diagnosing different kinds of outliers or different kinds of points in the regression model fit. So I can just say outliers can be the result of spurious or real processes. I mean, obviously, if you have an outlier that's just a data entry error, that is a different thing than an outlier that just happens to have a large x value and the model doesn't adhere well out in large x values. Outliers can have varying degrees of influence. They can conform to the regression relationship, i.e. being marginally outlying in x or y, but not outlying given the regression relationship. And then I just go through all those 4 points that we already went through right here, and you can read that yourself. Okay, so R has all these great influence measures that it does by default, and you can just do !influence.measures to see them and get the help file. So there's the standardized residuals, which is residuals divided by their standard deviations. Studentized residuals, standardized residuals divided by their standard deviations, where the standard deviations are calculated in a different way so that the studentized residuals follow a t-distribution. Hat values are measures of leverage. The DF fits are measures of influence of a point on prediction. DF betas are influence of a particular point on the coefficients. Overall change, Cook's distance is a measure of the overall change in across all covariates. And DF betas, I think I misspoke when I said that DF betas looks at individual covariates, where Cook's distance looks at all the covariates, kind of organized in the right way. There's a little typo there that I got to fix. Resid returns the ordinary resid here. This guy returns the ordinary residuals. And then this guy, if you just take resids and 1 minus the hat values, I noticed R doesn't do this automatically, but it's so easy, why would you care? Where fit is the linear model fit, that returns the so-called press residuals, okay, which are the leave one out cross-validation residuals. And so what I mean by leave one out cross-validation residuals, I mean the difference between the observed data point and the fitted data point, where the model was fit without that data point being included in the model fitting. So that's kind of like, I left out this point and now I want to see how my model predicts at this one point, and by maybe leaving one point out, I'm not going to impact how well I estimate the model, but now I have kind of a pure measure of prediction error. And there's lots of cross-validation strategies. I think you'll cover them in your machine learning class if you take the series. It is neat. I find it neat that you don't have to actually take out the point and refit the model to get these leave one out cross-validation residuals. That's a nice component of linear models. It's neat, I think. The proof is really neat too, but it's probably a little bit beyond the scope of the class, and we don't want to spend a week just going through the proof of how you get the press residuals. So how do I use all these things is probably what you're asking yourself. And the number one rule, I would say, is be wary of simplistic rules for diagnostic plots and measures. And I prefer to think of these tools as being context specific. So what I would hope everyone in this class would do is understand what the tools are trying to accomplish and to use them judiciously and smartly. A very important point is not all the measures have meaningful absolute scales. So you might want to compare certain measures of outlierness or influence or whatever across different data points, but you don't want to compare them across data sets. But what they do is each in turn is they kind of probe your data in different ways to diagnose problems. Think of yourself as you're a data doctor and you're trying to diagnose something, so you have all these different probes and tools that you're using, and that's what these little diagnostics are for. That's why they call them diagnostics. So anyway, residuals are, of course, the most important component of all the diagnostics, looking at residuals. And basically what you want is no kind of obvious systematic pattern in your residual plots. So you don't want heteroscedasticities, like non-constant variance. You don't want things that show obvious evidence of missing model terms. And you don't want things like temporal patterns. So if you were to plot residuals versus the order in which the data was collected, you don't want things like that. Residual QQ plots, quantile plots investigate normality of the errors because it's plotting the quantiles of the residual versus the theoretical quantiles of the standard normal. Leverage measures can be thought of as diagnosing. Those kind of measure the potential influence for leverage. So they only depend on the x's. They don't depend on the y's. They measure the potential for leverage. And some of the other measures, like the DF betas, measure the actual influence. But nice thing about leverage measures is they can often be useful for diagnosing data entry errors or kind of aberrant points. Influence measures, they get to the bottom line, kind of how does deleting or including this data point impact a particular aspect of the model. So the influence measures are things like the DF betas, that sort of thing. So let's just go through some cases. Here's a nice case right here. There's no regression relationship between x and y, but we have this one outlying point out there, right? So I just generated random bivariate noise and then threw a point way out there. So we get this regression line just by virtue of that. So this point has huge potential for influence that it actually exerts. Okay. That's the code. So I generated one point that was 10, 10, and then the x's and y's were otherwise just standard normal noise, R norm n, independent R norm n. That C isn't necessary right there. And then I put the AB line is the fitted line in there. So the point 10, 10 has created a strong relationship where there shouldn't be one. So showing a couple of the diagnostic values, that point, obviously, if you look at the DF betas, right, which are exactly the, so the DF betas are the coefficient, the difference in the coefficients between what you get if you leave that data point in versus you take it out. And so you can see, obviously, the slope coefficient changes dramatically if you include that one point that's driving the whole relationship versus you take it out. The hat values are, as always, a measure of potential for influence, and so this guy has, of course, a giant hat value. Okay, so now let's consider a case where there is a regression relationship, and see in the point, which is sort of outlying here, which is sort of outlying in terms of its x and y values, but still quite well fits the regression relationship. So in this case, if we do the DF betas, you can see that that point is generally in line with the other ones, not outrageously so, but the hat values, its hat value is quite a bit bigger than a lot of the other data points. But notice, just one thing I want to point out is this outlier is only at the x's and y's are bivariate normal on that kind of scale if you look at the code, but this guy's only at say 5, 5, whereas this other one was quite far out there at 10, 10. That's why the hat value for that other one was so much larger. So let's go through an example of looking at residual plots. And Stefanski in this American statistician paper had this great kind of startling example, several examples, and he created this mechanism for creating them on why it's useful to look at residual plots. So here's the data. I grab it from his server, and don't everyone hit his server. Instead, kind of read at the same time. Read the paper first, and then pairs just does all pairwise scatter plots. All right, so here's all the variables, and you obviously don't see very much in the pairs plot. In this case, there's a ton of overplotting. If you do a standard linear model where it takes this first variable and regresses it on everything else, and then just grab the coefficient table, you see a bunch of highly significant p-values. Imagine if you were to stop there. Okay, but there's clearly an evident aspect of some pattern in the residuals, because if you say fit the model and then plot the residuals versus the predicted values, which if you have a multivariate relationship, if you have a multivariable regression model, it's often useful to put the predicted values versus the residuals. In this case, there's obviously some sort of pattern there. That's the O-ReLL. So let's look back at the Swiss data and see what these different plots are trying to accomplish a little bit. So the residuals versus the fitted values, those are, you're looking for any sort of pattern. Same thing with the fitted values versus the standardized, the scale location plot here, where it's plotting a function of the standardized residuals. The normal QQ plot is you're trying to figure out normality of the errors by plotting the theoretical quantiles of the standard normal distribution by the standardized residuals. And you know, it's a little bit difficult to tell because of the scale, but these are the labeling of the points of some of the provinces. And then residuals versus leverage, that's where you want to look at, you know, the comparison of fit at that point versus the sort of potential for influence of that point. So this is also a very useful plot to look at. I would also suggest for everyone in the class to go through the example of looking at the DF fits and the DF betas and Cook's distance for all of these for this data set. And you know, what you're interested in looking at are whether or not these measures, you know, whether or not one of the particular provinces seems influential or has a particular kind of large effect, and then you would want to sort of dig into that data point in specific.